Hello students, and welcome to the lecture on Central Processing Unit, or CPU. After this lecture, we will be able to learn the following objectives. Explain the introduction of CPU. Discuss the history of evolution of CPU. Define the addressing modes. Explain relative addressing and stack addressing. Understand the concepts of interrupts. Describe the instruction and execution interrupt cycle. Let's start with the introduction of Central Processing Unit, or CPU. In order to work, a computer needs some sort of brain or calculator. At the core of every computer is a device roughly the size of a large postage stamp. This device is known as the Central Processing Unit, or CPU for short. This is the brain of the computer. It reads and executes program instructions, performs calculations, and makes decisions. The CPU is responsible for storing and retrieving information on disks and other media. It also handles information from one part of the computer to another, like a central switching station that directs the flow of traffic throughout the computer system. The CPU resides inside a box known as the system unit, along with various support devices and tools for storing information. Just think of the system unit as a container for the CPU. The system unit case, that is, the metal case itself, can either be short or wide. It usually sits on top of the desk, often underneath the screen, or it can be taller and narrow. It generally sits underneath the desk and is referred to as a tower case. Let's now discuss the CPU. CPU stands for Central Processing Unit. This is pretty much the brain of the computer. It processes everything from basic instructions to complex functions. Anytime something needs to be computed, it gets sent to the CPU. Every day it is computed. One would think that the CPU would need a break after a while. But no, it just keeps on processing. The CPU can also be referred to simply as the processor. The CPU is also known as processor, computer processor, microprocessor, and central processor, and the brains of the computer. The CPU will repeat these steps and continuously carry out these operations. A lot of people have a wrong impression that a CPU is a command center. They believe it generates all of the commands and the computer will follow those commands and operate. Actually, the CPU will not generate commands for the computer. Central Processing Unit, otherwise known as a processor, is an electronic circuit that can execute computer programs. Both the miniaturization and standardization of CPUs have increased their presence far beyond the limited application of dedicated computing machines. Modern microprocessors appear in everything from automobiles to mobile phones. There are two major kinds of instruction-level parallelism, or ILP, in the CPU. Both first used in early supercomputers. One is the pipeline, which allows the fetch, decode, execute cycle to have several instructions underway at once. While one instruction is being executed, another can obtain its errands, and a third can be decoded, and a fourth can be fetched from memory. If each of these operations requires the same time, a new instruction can enter the pipeline at each phase, and, for example, 5 instructions can be completed in the time that it would take to complete one without a pipeline. The other sort of ILP is to have multiple execution units in the CPU duplicate arithmetic circuits, in particular, as well as specialized circuits for graphics instructions or for floating point calculations. With this superscalar design, several instructions can execute at once. History of CPU. The first CPU chip was created by Intel back in the early 70s. Besides Intel, companies such as IBM, Motorola, Texas Instruments also joined the CPU market and started designing their own CPUs. At that time, the CPU was so simple that it could only be used on a calculator. During the 1980s, the CPU had a great evolution. The size increased from 4 bits to 16 bits, then all the way to 32 bits. Its functionality and capability also had a substantial improvement, so they gained a great variety of applications. However, the cost for a CPU declined, and that made the home computer possible. In the 90s, Intel played an important role. They developed the well-known Pentium series processors for home computers. Meanwhile, AMD, or Advanced Micro Devices, joined the game and started the match with Intel. CPU building blocks. The CPU itself is an internal component of the computer. Modern CPUs are small and square and contain multiple metallic connectors or pins on the underside. The CPU is inserted directly into a CPU socket, pin side down, on the motherboard. Arithmetic Logic Unit, or ALU. The arithmetic logic unit is the brawn of the computer, the device that performs the arithmetic operations like addition and subtraction, or logical operations like and, or. An ALU from 4 hardware building blocks. Because the MIPS word is 32 bits wide, one needs a 32-bit wide ALU. Let us assume that one will connect 32 1-bit ALUs to create the desired ALU. Therefore, start by constructing a 1-bit ALU. The ALU performs arithmetic calculations and data manipulation, for example, comparisons, sorting, combining, etc. The computer's calculator is a part of the CPU known as the arithmetic logic unit. It holds data and instructions, which are in current use. Control unit. The control unit, or CU, extracts instructions from memory and decodes and executes them, calling on the ALU when necessary. This is done by the control unit of the CPU, which sends command signals to the other components of the system. Some important points related to the control unit. The control unit directs the entire computer system to carry out stored program instructions. The control unit must communicate with both the arithmetic logic unit and main memory. Memory unit. The memory unit is the part of the computer that holds data and instructions for processing. The main functions of memory unit are, although it is closely associated with the CPU, in actual fact it is separate from it. Memory associated with the CPU is also called primary storage, primary memory, main storage, internal storage, and main memory. RAM. RAM stands for Random Access Memory. This is really the main store, and it is the place where the programs and software get stored. If the central processing unit needs to store the results of calculations, it can store them in RAM. Random access memory can have instructions read from it by the CPU, and also it can have numbers or other computer data written to it by the CPU. When one switches a computer off, whatever is stored in the RAM gets erased. ROM. The ROM stands for read-only memory. The CPU can only fetch or read instructions from read-only memory, or ROM. The ROM comes with instructions permanently stored inside, and these instructions cannot be overwritten by the computer's CPU. The ROM memory is used for storing special sets of instructions, which the computer needs when it starts up. When one switches the computer off, the contents of the ROM does not become erased, but remains stored permanently. Therefore, it is non-volatile. These are kept in the main store or memory. Did you know transistorized CPUs during the 1950s and 1960s no longer had to be built out of bulky, unreliable, and fragile switching elements like vacuum tubes and electrical relays. Now we will study the addressing modes. Addressing modes provide different ways for accessing an address to given data to a processor. Operated data is stored in the memory location. Each instruction requires certain data on which it has operates. There are various techniques to specify the address of data. These techniques are called addressing modes. Indirect addressing modes. In the indirect addressing mode, the instruction specifies a register which contains the address of the operand. Both internal RAM and external RAM can be accessed via indirect addressing mode. The effective address of the operand is the contents of a register or main memory location, location whose address appears in the instruction. Indirection is noted by placing the name of the register or the memory address given in the instruction in parentheses. The register or memory location that contains the address of the operand is a pointer. When an execution takes place in such a mode, instruction may be told to go to a specific address. Once it's there, instead of finding an operand, it finds an address where the operand is located. Immediate addressing mode. In the immediate addressing mode, direct data is given in the operand, which moves the data in an accumulator. It is very fast. Index addressing mode. In the index address mode, the effective address of the operand is generated by adding a content value to the contents of the register. The mode is called index address mode. The address of the operand is obtained by adding to the contents of the general register, called index register, a constant value. The number of the index register and the constant value are included in the instruction code. Index mode is used to access an array whose elements are in successive memory locations. The content of the instruction code represents the starting address of the array and the value of the index register, and the index value of the current element. By incrementing or decrementing index register, a different element of the array can be accessed. Register mode. The name, the number of the CPU register, is embedded in the instruction. Displacement mode. Similar to index mode, except instead of an index register, a base register will be used. Base register contains a pointer to a memory location. An integer constant is also referred to as a displacement. The address of the operand is obtained by adding the contents of the base register plus the constant. The difference between index mode and displacement mode is in the number of bits used to represent the constant. When the constant is represented by a number of bits to access the memory, then one has index mode. Index mode is more appropriate for array accessing. Displacement mode is more appropriate for structure, records accessing. Relative addressing. For relative addressing, the implicitly referenced register is the program counter, or PC. Base register addressing. The reference register contains a memory address, and the address field contains a displacement from that address. Indexing. The address field references a main memory address, and the reference register contains a positive displacement from that address. Stack addressing. A stack is a linear array or list of locations. It is sometimes referred to as a pushdown list or last in, first out queue. A stack is a reserved block of locations.
In 8051, we have mainly 9 addressing modes, which are immediate addressing mode, register addressing mode, indexed addressing mode, to name a few. First of all, we'll discuss immediate addressing mode. In this mode, our operand is an immediate data, which is constant. As you know, in assembly language, immediate operands are preceded by a pound sign as shown. For example, we have instruction move A, #6AH, where 6AH is the immediate operand. As you can see, the accumulator is holding 6AH, the immediate value. The next mode we are going to discuss is register addressing mode. In this mode, one of the operands is a register holding the data to be manipulated. The source and destination must be of same size. For example, in this instruction, the value stored in the register R4 is copied to the accumulator. Coming on to direct addressing mode. In this mode, directly, the address of RAM location is given in the instruction. It can access RAM locations from 00 to 7FH. For example, as we can see, RAM location 04H stores the value 1FH, which is copied into the accumulator through the given instruction. The next addressing mode we are going to discuss is indirect addressing mode. Here, register is used as a pointer to data. The register holds the address of the RAM location containing data. @ sign is used before register indicates that the register is used as a pointer. For example, here register R0 stores the value 20H. Using this instruction, the value stored in the memory location 20H is copied to the accumulator. As you can see, accumulator contains 2FH contained in 20H. Indexed addressing mode. This mode used a base register, either a program counter or a data pointer, and an offset, generally the accumulator. Jump tables or lookup tables are easily created using indexed addressing. For example,